is we have built a lot of concrete structures. Now, how do we make sure that those structures actually last longer? And so in that aspect, we will also have to develop durable repair strategies. And for, let's say, if we want to increase the structure for about 20 more years, how do we do the repair? And then let's say you reach a stage where you really cannot repair, or for whatever reasons, you have to demolish the structure. If you demolish, how do we use that waste from the demolition? How can we reuse that waste? And then also policies required for managing such waste, because most often policies actually don't help much, or sometimes because of lack of a particular policy, you are not able to use a good construction material or a good waste material. So all those aspects we will be looking at. So this is all about our center. How do we, my computer stopped working. Yeah, do you see my screen?
Yes, but
yes,
you need to
my screen became blank.
Show mode.
So, yeah, can you see now? Yes. Hello?
yes.
Yes.
Yeah, okay.
Yes, we can see now.
Now for today, I just want to brief you on what our Center of Excellence on TLC2 does. So we work all on materials and management aspects. And now today's topic is mainly on looking at how do we build durable concrete structures, or rather, how do we control corrosion in concrete structures. So I'll be talking about materials aspect. How do we choose a particular material which will help you in building long-lasting structures? And we will then talk about cover concrete and its properties. What are the key factors which, why do we worry about cover concrete? And then a concept called MXDY concrete I will talk about. And then how do we, make sure that the water which we use for concreting are good, because that also plays a significant role. And then finally, if time allows, I'll talk about galvanic cathodic protection. So this is the outline for today's talk. So if you're most often, we worry a lot about corrosion in concrete structures, mainly because it costs us a lot. And it's also make the structure unsafe after some significant amount of corrosion has happened. So this is something which we all are worried about. And how much does it really cost? It's about 3 to 5% of the gross domestic product is what the cost of corrosion is estimated to be. Now, out of this thing, I can confidently say about 50% of that is because of the deterioration or corrosion of concrete structures. Okay, concrete infrastructure that plays a significant role or significantly contribute to this cost of corrosion. Now, if you look at this graph here, you can see some places it's more or less it's around 4%. You can say, that is something which we have to worry about. And if we can divert or use this money for good construction, it will be really, really helpful. So our objective is to reduce this cost of corrosion to the maximum or to the minimum level possible, so that we can use that money for other things. Now, one which I would like to mention is the importance to be given for the material science or the construction materials aspect and the construction process or construction technology aspect. Okay. Today's lecture will be more on the materials aspect. And why I'm showing this pie chart here is most of the structures are designed well in terms of structural design. And because of that, probably because of that, we see the gray region on the left side, only about 12% of the failure is because of structural design related issues. But what we are seeing is about 40% of the failure is because of the materials related issues, like concrete. Not a good quality concrete is used, or not a good quality steel is used, or construction materials quality. So if you can focus a little bit more on construction, the quality of the construction materials, we will be able to build better structures. but we need to improve our attention towards that. In addition to the structural design and analysis aspects. Construction is also another important area, especially when you're talking about large scale structures. We really have to now focus on materials aspect and construction aspects. Combining these two, it's almost 65% of the failure. So if we can improve on the materials quality and construction quality, we can really reduce the number of structural failures. Okay. Now, when I talk about service life, there are different phases for service life of concrete structures. Okay. The first phase, imagine, look at this, this sketch here. You can see, assume this as a cover depth. Okay. This is the reinforcement, the black circle. And this blue line, blue arrow indicates the movement of the chloride ions from the surface. This is the surface. So what you're seeing here is the cover concrete. And as you see, the red circles are moving towards the steel, which is embedded inside the concrete. So this is basically diffusion of chlorides. So if you're talking about a coastal structure, a coastal bridge or something, or a building near the shore, you have such problems where chlorides are coming from either through the airborne or through the soil. Somehow you have chloride attack on the concrete surface, and that enter the concrete surface, and then it slowly penetrate into the concrete and reach the steel reinforcement. When the chloride starts getting at the steel reinforcement and it builds it gets deposited on the steel surface. And when it gets deposited on the steel surface, and that concentration over here reaches a value which we call chloride threshold, then the steel starts corroding. So this is the point when that steel starts corroding in the time scale, or the horizontal axis here is the time axis. Vertical axis here is the damage level. So until the corrosion of steel starts, you don't see any damage. Okay. Or corrosion induced damage is our focus today. Now, once the steel starts corroding, then in few years, you will see that there is significant cracking, spalling, etc. And this dashed line over here indicates that the damage level has reached a critical level. Then what you do, you will actually go for a repair. That way your damage level is reduced. Then again, the structure is in the same condition, and if the durability, if the repair is not done in a proper way, you will again, after few years, you will go and do the repair in the same place. So multiple repairs you will keep on doing, which is going to cost you a lot of money. Now we have a technology where we call galvanic cathodic protection, where we can actually go for a repair which will really last for 15, 20, 25 years. It's possible. Okay. So that's what this long green line is showing. I will briefly talk about this cathodic protection in the last stage of this presentation today. So this is essentially what is service life of concrete structures. 3 phases: initiation, propagation, and repair. Main focus today is on initiation phase because that is the longest phase in the life of a structure. So if you're talking about designing something for 100 years or 50 years, you need to make sure that this initiation phase is 100 years or 50 years. Okay, we don't really consider the propagation period in our design or service life design. Now, to design such a structure, you need to worry about the cover concrete and also the steel cementitious interface. So both steel and concrete are very important. You have to have a balance of good quality concrete and good quality steel. Then only you will get really the long life for the structure. Now, when you say good quality concrete, main thing is, see, for all structural capacity aspects, we use the core concrete. So look at the picture on the left side. The black, this thing is the reinforcement. You can see the black rebar, and the concrete inside the rebar is a good quality hardcrete. We call it hardcrete or corecrete. Now, if you do not cure the concrete very well, then you have a problem that the surface or the peripheral concrete, you can see my cursor here, red color cursor. So the surface of the concrete will be more porous in nature, maybe of poor quality, which will affect the durability. It means if it is poor quality concrete on the surface, what will happen is this deleterious agents like chloride, oxygen, carbon dioxide, moisture, etc. can penetrate through the cover and reach the bar and create problem. Problem means create corrosion. So what we are saying is like, for durability, the cover concrete is very, very important. Whereas for strength related aspects, the core concrete or hardcrete is important. So we have to make sure that the cover is also very, very important. Towards the end, I will talk more about the cover concrete and curing. Okay. Now, to also make good quality concrete, what we do, we put mineral admixtures, we put chemical admixtures, and we try to minimize the amount of cement. When you talk about good quality concrete, this is something very important. Usually people will say add more cement and make the concrete better. It is not like that. We have to increase the amount of aggregates or sand or coarse aggregate and fine aggregate in the concrete and minimize the amount of cement. That will be a better quality concrete. Now people will say when you minimize the amount of cement, the concrete will not flow properly. What you do is you use chemical admixtures to make the concrete flow. Super plasticizers is one material which is widely used. Okay. So this is the idea. Like, you have minimal amount of cement in the concrete, and to make the concrete flow, you use chemical admixtures. And to enhance the property in the cement itself, if you can include more of materials like fly ash, slag, etc., then you will get a very, very good quality concrete. Now you say, oh, you put all these materials, and if you do not cure the concrete, you will not get what you are aiming for. So all these materials plus appropriate or adequate curing is very, very important. Then you will get desired workability, desired strength, and desired durability. So all three can be achieved if you use good quality materials and in appropriate dosage, and also cure the concrete very well. Now today we have a lot of materials available in the concrete structures, and every day or now and then you will see different type of steel is available, different type of chemical admixtures, different type of cementitious materials, etc. are available in the market. Now with all this, if you really want to establish what is the service life, one parameter is very critical, which is chloride threshold. Okay. Now conventionally or traditionally, we have been used this 0.4% by weight of binder as a critical chloride threshold, which is the amount of chloride required to initiate corrosion. Now, this number might change as you change the type of concrete which you use and as you change the type of steel which you use. Okay. Now, I'll talk to you about that a bit later. Now, before going to the next slide, I want to also show you the advantage of using different chemical admixtures, different mineral admixtures or supplementary cementitious materials. Look at this blue markers here. This is OPC, ordinary Portland cement. The resistivity of that concrete made with ordinary Portland cement is in the range of 10 to 20. You can see here very few numbers, very few blue markers in the around 20. This is a logarithmic scale here. Now, when you mix a little bit of fly ash or slag, etc., you can see that there are a lot more numbers in the higher range. Or in other words, the resistivity of the concrete has significantly increased with the use of fly ash, low water binder ratio, and superplasticizers. So if you mix the concrete or come up with a proper mix design where you maximize the use of or optimize the use of supplementary cementitious materials, superplasticizers, etc., you can really get a highly resistive concrete, which will help in resisting the penetration of chlorides, moisture, oxygen, etc. into the concrete, which eventually help us in building durable concrete structures. Now, I was talking about the chloride threshold. So here we have done a significant amount of study in looking at how these different chemicals and mineral admixtures or SCMs will influence the chloride threshold, and also in particular chloride threshold of the pre-stressed concrete. That is also something which we looked at. And you can look at this graph and see that it is not 0.4. This vertical red line, it's showing the conventional value of 0.4, whereas we found that it need not be 0.4, it could be less than, more than, all that. There's significant variation in the chloride threshold. One important point is for pre-stressed concrete, the chloride threshold is significantly less than the other system. And also for rebars which are coated with fusion bonded epoxy material, there also you have this green color bar which you might have seen in many construction sites. There also you have significant reduction in the chloride threshold. What it means is such systems could start corrosion at a lower chloride level, which is something one has to look at. Now, if you talk about increasing or enhancing the service life, we have to increase the chloride threshold. Okay, somehow, one way or the other, we have to increase the chloride threshold. Other way is you reduce the speed by which chloride reaches the steel surface. Two things. One is reduce the speed by which the chloride penetrate through the concrete cover and reach the steel surface. The other thing is increase the amount of chloride required to initiate the corrosion of the embedded steel. So this one way of doing that is to increase the chloride threshold is to use something called corrosion inhibiting admixture. What we have found is this corrosion inhibiting admixture will improve the passive film which is formed on the steel surface. And what is passive film? Passive film is a very, very thin layer, which could be, the thickness could be just in few angstroms. Okay, a very thin layer which is formed on the steel surface, which protects the steel from further corrosion. Okay, now when you use this corrosion inhibitors, that thin layer becomes better, or it can resist more chlorides. So essentially you are increasing the chloride threshold of the steel reinforcement. Now, how do we put this corrosion inhibitor? It is a chemical which is available. You can buy it in the market, and then you mix that with the concrete and then use the concrete. That's how we do. Now, this is a study which we have done where we have clearly found that the use of inhibitors can enhance the chloride threshold, and eventually the effect of that is increasing the service life by 3 times. This study showed 3 times, let's say at least 2 times. Okay, so definitely there is a benefit in using corrosion inhibiting admixtures as an integral. As an admixture means you will mix that with the concrete, and the concrete will help in increasing the chloride threshold of the embedded steel. That means the service life can be increased by 2 to 3 times. So let me skip this particular slide here. So this is again corrosion initiation time. You can see the black one, it's here OPC with no inhibitors. Let's say you get about 50 years. This is a parametric study. So you don't look at this absolute value on the left side, but look at the percentage increase in the service life. So let's say you get 50 years in case 1, which is controlled scenario. Now you put some fly ash in the concrete and no need of inhibitors. You will get still some about 90 years of life, almost doubling the life, right? Now, if you put fly ash and a little bit of admixtures, you get a little bit more life. Now, if you put, so this here in the blue case also, you can see a little bit of fly ash and corrosion inhibiting admixtures, and that you get around 120 plus years of life. So significantly, the message from this slide is that when you use fly ash or slag, those kind of SCMs, supplementary cementitious materials, that's what we call it. When you use such materials, the service life of the structure can significantly increase. Significantly increase, not like increasing by like few percentage, no. You can see here from 50, I'm able to even get up to about 120 plus. So more than double is the point. So message here is there are two parameters which we have to worry about. One for the concrete and one for the steel concrete interface. Look at the right side. This is where I started the discussion with. Same chart. You have these red circles, which are the chloride ions penetrating or diffusing towards the steel reinforcement. And this is the steel reinforcement. So the speed by which this chloride ion penetrate, if you can reduce that by using SCMs, you get more service life. That is one aspect. Other aspect is chloride threshold. The amount of chloride required at this point at the surface of the embedded steel, if you can increase that, then also you enhance the service life. So here by using the SCMs, we are reducing the speed of penetration of chlorides, and by using the inhibitors, we are increasing the chloride threshold value. So this is a synergistic effect. Both parameters are, the chloride speed is reduced and at the same time demand is increased. So then you get really long service life. How to do that? Now, selection of the reinforcement, how do we select that? So this is something which is happening in many parts of the world. Lot of people are using this kind of epoxy coated bar. I don't know if in Nigeria if it is used, but many parts of the world I'm aware of use of such type of rebars. We found that many a time the rebars are actually scratched, or the coating on the rebar is mechanically damaged, or when they get exposed to sunlight, they undergo UV induced damage, ultraviolet rays. So they look at the map, world map here, looking at, you can see this region here, and you have significant, very high UV index. For most part of the world, you can see that. So where you have high UV index, again, you may not want to use a polymer-based, coating for the rebars, because delays in construction is very common. Now, how long it took? We did some study here. We found that within about a month, like within about 10 days, the second picture here, there are a lot of cracks, micro cracks in this. When we expose this to UV radiation, this coating, we found a lot of crack formation in the coating. And that is not something good, because once you have a crack like this, then the moisture, oxygen, etc. can penetrate through this crack and then reach the embedded steel surface and cause corrosion. Okay, what you're seeing here is epoxy coating, the microscopic image of the cracked epoxy coating. These four images are like that. Day 0, no cracking. Day 10, a lot of cracking. I don't know if you can see in the screen, but it's very fine cracks through which water molecules, oxygen molecules, etc. can penetrate. Day 20, wide crack here, you can wider crack here. So this is something which is telling us that the use of epoxy coated bar should be avoided if you cannot prevent cracking and exposure to sunlight. Okay. So what we found quantitatively is that if there is no damage on this bar, like very perfect, pristine, perfect epoxy coated bar, then you will get very long time, a very long service life, 150 years in one case. But unfortunately, most of the structures, they get exposed to scenarios like this. So this is an epoxy coated bar exposed to sunlight. Definitely it is going, you will have cracks on the coating. And then if you have a scratch damage, the blue curve here, this also will lead to. So one of this, if you have scratches like this, it will start corroding. And it is essentially a crack, wide crack. So when moisture gets in there, you have chances of crevice corrosion in those or on those rebars. So essentially the message here is that there could be significant reduction in the anticipated service life if the surface coating is damaged, through either by mechanical damage or UV induced damage. Okay, somehow if there are cracks or scratches on the epoxy coating, it's better not to use that. Okay. Now, other thing which is coming up in the market now is something called continuous galvanized rebars. Or before that, I'll talk about this. So this is the galvanized steel on the left side, which you can see that which is known for its corrosion resistance and all that. But unfortunately, it is not much used in the market because of the cost factors. Okay, it's because of this thick galvanized the zinc layer which you have here. As you see here, this is the steel part in a galvanized bar, batch galvanized rebar, BGR. So where you can see steel here, and then this is the galvanized coating or the zinc layer. Okay, a mixture of zinc and iron. Now, point here is this is very costly. So now the industry is coming up with a new product which is called continuous galvanized rebar. Only about 4 or 5 countries in the world is making it today, but I am sure this is going to be the future. So you can see that thinner layer of galvanization or thinner layer of zinc, which is actually giving excellent ductility and good abrasion resistance and very good metallic bond with the substrate steel. And on top of all that, because of the zinc, it is very, very good in corrosion resistance. Okay, so this is something, a new thing which is coming up. And what is the advantage of this? If you go with galvanized steel, there is a possibility that your service life of the structure can increase by 2 to 3 times. Okay, I mean, if not service life, at least chloride threshold will be significantly higher, 2 to 3 times, and associated service life increase is possible. So you can see here, if an uncoated steel is used, the red curve here, let's say you get about 25 years of service life. If you use galvanized steel, there is a possibility of getting a service life of from 50 to 75 years. That's very, very useful. Now, one message which I want to tell you is when you talk about coating for reinforcement, don't look at, only look for a coating which will give you very, very good abrasion resistance, because at a construction site, we don't treat rebars like babies. We throw the rebar, we drag it, we walk over it, we run vehicles over it, all sorts of rough handling happens. So we should make sure that the bars, the coating don't get abraded or damaged in a mechanical damage doesn't happen. On top, we also should make sure that it is UV resistant, the coating. And also it should be very good resistance against the chemical nature of the cement or the concrete itself. So all these have to be considered. When we look at all these things, today, at least based on whatever, techno-commercial aspects, when you look at it, I think going for a metallic coating is better than going for a non-metallic coating, which may have poor abrasion resistance, poor UV resistance. So with all this, we have also, come up with a set of nomograms, which is like a design chart in the structural design book. Here it is a durability design chart. Okay, so which is something which I find very useful, because you can just print it on a piece of paper and then you can start saying, okay, what type of concrete I should make for getting a particular service life. So as I'm speaking, I have shared this presentation to Professor Kolavale, so you can, take this thing and print it out and then see whether you can use this for your next concrete design. So how do we do this? We go, let's say we start from the top left corner. Okay. Now I'm a structural engineer. I want to say, okay, in 100, I'm designing for a 100-year structure. Let's say a major bridge in a coastal area, or designing for a 50-year life or something like that. So if it's 100-year structure, assume that. As a design engineer, I will say, okay, I'm able to accept 20% failure in 100 years. 100th year. So I start from here. I say, okay, my cover depth can be 70 mm. Okay, a major bridge exposed to seashore or something like that. I'll take a 70 mm cover. And then I draw horizontal line. And here in this quadrant, I'll pick one of the line based on the type of cementitious system which I use. This is the bind. Okay. Now, let's say I pick this C1 point, okay, which is 50% slag or fly ash, OPC, corrosion inhibitor, this kind of mix. I can go with this this graph here. From there, this up to here, this structural design office will decide. Then I come down and tell that, okay, my concrete should have this diffusion coefficient, this curve number 3, I will pick, and then go horizontal, and then this is the 100-year. So if I want 100-year life, my cover depth is 70 years. I pick this material 1, or the cement binder choice is 1. And then I say on the field, the person on the field has to ensure that the concrete has very good diffusion coefficient. Okay. So this is a concrete property which is decided by the person on the site. You can do any design in the paper in the office, but at the end of the day, if it doesn't happen on the site, there is no use. So how do we ensure that? We bring in quality control measures, right? Now this to test the diffusion coefficient, it will take 2 months for me. So by that time, structure is already built and it's too late for that. So what do? We say that there is another test which is very simple to do and which is we call resistivity test. 4-probe, Wenner 4-probe resistivity test. So we have come up with a relationship between the DCL and the resistivity. So here you can use this curve here and say, okay, if my DCL is going to be the number 3, which is the D3 into 10 to the power of minus 12, the corresponding resistivity will be something. Then I put that resistivity as the target. I say, for example, in this case, I'm saying, okay, 30 is my target to electrical resistivity. Then my concrete will be good. Now, engineers can do this test on a cube, or even on a structure, they can do this testing and say, find that, okay, this is the resistivity. So every concrete compressive strength specimen, when you do testing, you do a resistivity test on that specimen. Wet resistivity test. This should be done when the concrete is wet, not when the concrete is dry, because when the concrete is dry, you will get very high numbers anyways. Okay. So the idea is wet resistivity of the specimens. Now, when you do this, you can say my concrete is mx dy. M stands for the mechanical property and D stands for the durability property. And resistivity is a representative representative parameter for ensuring good for ensuring durability. So we have implemented this in one of the projects here. You can see the bridge on the left side where the outer 2 spans were done with M40 concrete. Kolavolai, over there, do you use M value or how do you go by?
In Nigeria,
The compressive strength, you use M or how do you?
I will
M or
use
C.
CU.
C.
CU.
C, right?
We use C. We use C40.
C, yeah, okay.
Yes.
So, yeah, here in India, we say M40 for 40 MBA characteristic strength. So in the middle span here, when the project started, we were able to, by the time they constructed the middle span, we were able to convince them, convince the authority that, okay, you had to go for this durable concrete. And we, were successful in convincing and then making this PSC or slag-based concrete for this. And this is the mixed design over here. So we tried 4 mixed designs and proved that the slag concrete with the D30, that is 30 is the minimum resistivity for that concrete. So we proved that it is possible. We did a lot of testing on the field, on the actual bridge elements. We took cores from the bridge element. This is actually the approach road for the bridge. We took samples from the field cast concrete, and what we found is when you go for slag concrete, you are able to get 125 years as the service life. Whereas in the OPC concrete, it was coming to be 31 years. So huge difference. So idea is that, so here also you can see this graph here, the speed by which chloride will penetrate. In the OPC concrete, it's very high, whereas the slag-based concrete, it was very, very low. So this is the advantage. You are reducing the ingress rate of chlorides and also increasing the chloride threshold. And you eventually with the admixtures like corrosion inhibiting admixtures, etc. So you are able to get very, very long service life. That means if this 125 here means that for 100 years at least, let us say, forget the calculation, at least we'll get 100 years life where you don't have to worry about corrosion. So this is something which I would like to emphasize, that use of supplementary cementitious materials really, really enhances the life of concrete structures. Okay. Now, other thing which we often neglect is the cover depth, which I believe is probably the most important thing which one should worry about. See, the advantage of having a good cover in a concrete structure. So look at this box here on the right side in this study. 30 mm cover, let's say you get 20 years life. 40 mm cover, you get 32 years life. 50 mm cover, you get 46 years. So thumb rule is for every 10 mm, you can get about 65% increase in the life, service life. But it doesn't mean that we can keep on increasing the cover, because it will crack, the concrete will crack. So you have to optimally design that. Now, point what I'm trying to make is whatever is specified, make sure that it is actually achieved on the site. So here is an example where I'm showing a structure where cover was not very good. Okay, what you're seeing here, a concrete column in an apartment building. And you see this one, when we removed the plaster from here, we found that the concrete is on one side it is good and other side it is very, very little. So in the close-up, this region is shown here, where you can see 2 inches of plaster material on one side. That means on the other side of the same column, it will be much less. So there is a significant variation in the cover. Cover depth is not adequately provided in many, many cases, and which lead to significant corrosion, early corrosion issues. And so if here, when we opened it up, you could see that a lot of cracking, this hairline crack, very, very, fine cracks. But when you opened up, you could see the significant corrosion here. So this is the same column. When you open the column on one side, it looks like this. You go to the right side, like near the staircase here. You look from the right side, you can see very hairline cracks here. And then when we opened this plaster, this shaded region here, we opened it up and then you could see that significant corrosion. Where is this? Why is this corroding here? Because you remember, in an apartment complex, people will mop or keep the area clean. So every day you will provide water. Now that water is through capillary rise, it is reaching to about 1 meter height, and you can see very clear corrosion. So cover is very, very important. The quality of the cover, it's extremely important. Now, people might say that all the mistakes in the cover is covered up by putting proper plaster. This is a photograph to show you that plaster has no role in preventing or no role in enhancing durability. It's just a cosmetic cover, only cosmetic. You see here, in 8 years, in one of the structure where we visited, and we found that this is the plaster region. Okay, in 8 years, this was tested in 8 years because the corrosion already happened in 8 years after construction. So we went there, inspected, we found that concrete was very good quality concrete, but cover was not adequate. And the plaster is completely carbonated. This is a phenolphthalein test, So plaster really doesn't resist any, it just carbonates very, very fast. So message what I would request you is, try to avoid plastering if at all it is possible, because then you will ensure that the concrete is of good quality. And when concrete is of good quality and adequate thick concrete cover is provided, then your structure will really last. Now, how do we ensure that this good quality cover is provided? Usually, I've seen many places where plastic cover blocks are used. My suggestion is not to use that. Okay? Because these plastic cover blocks might when the concrete starts shrinking, it might open up over there where the plastic is there, and then there you have a direct pathway from outside towards the steel through which water, oxygen, etc. can penetrate. And other thing is there are cover blocks in the market which looks very good and smooth surface. So you may not have proper bonding with the surrounding concrete. Cover has to bond well with the surrounding concrete. That is why even plastic may not be very good. Okay. So now we are recommending cover blocks which looks like this, where you can put this circular disc. So we should call it disc, not cover block, but cover disc. Okay. Cover disc we can provide, and then these are indicating the disc. If you are talking about a column, provide the disc on the stirrups, the horizontal or the lateral reinforcement. Okay, not the longitudinal reinforcement. So provide this cover block on the exterior or outermost steel reinforcement. So I think it's understandable. I think so. This is the cover block. These blue things over here is the cover block. These are the shear stirrups. You provide it on them. Advantage of having this disc with the hole in the center is that it cannot be misplaced. When you have cover blocks like this, even if you tie them very well, it could be misplaced. Okay, so okay. Now, cover is something very, very important. So we have to ensure that the concrete cover is very, very good and of very good quality. Okay. So this is a bridge which was just built 20 years ago. Okay. And it was repaired once in 10 years and then again ready for the next repair. So this is something which we have to really avoid. So cover, if it is very good, you will not have this kind of problem. So what type of water which we should use? Make sure that water is potable. Use the same water which you can give for which you drink can also be given for the concrete, if at all, if it is possible. If it is not possible, make sure that that water is treated well so that the chloride content and sulfate content is very limited in the water. In this case, I think I'll stop here because it's already 4:30. So.
All right. Thank you so much, Prof. It's been an engaging session with you. And seriously,
I have more stuff, but I can cover that later.
Yeah, I wish you could go on and on and on and on. I've picked up a lot of lessons from your presentation, and I think one of them that stands out for me is the fact that we should give to concrete the water that we want to drink. Yeah. Thank you so much for that. Now we'll move to the question and answer session. That will take place for about 10 minutes. Members, if you have questions, please indicate by using the hand icon. So please, so that I can call us to make our questions known. Thank you very much. Question and answers. Okay, Dr. Maruf Olalekan Yusuf, your hand is up. Your question, please.
Yeah, thank you very much, Professor Pillai. My name is Dr. Maruf Yusuf. Thank you so much for this presentation. It's quite engaging. But my question is, did you try to look into the impact of sulfate on the expansive expansion of concrete in foundations? And knowing fully well that C3A is chloride binding. However, when it meets sulfate ions, it begins to form late entringites that form expansion of concrete. Did you try to correlate the use of type 5 and type 1 plus pozzolanic material?
Yeah, we have not me. I have not done that work, but Professor Manu Santanam here, our group has done a lot of work on that. And it's very clear that when we use SCMs, the sulfate resistance really increases. We have seen that in many of our studies. So that expansion property, which you see it kind of reduces because it's very dense material or very compact. So sulfates find it difficult to enter the concrete when you go for SEM based concrete.
All right. Thanks very much, sir. Any other question? Any other person who
I have
wants
a
to?
question. Maybe I can
All
add.
right,
Sorry.
sir. Professor Olafemi. Thank you, sir.
Okay. Hello,
Hi,
Prof. Pile.
how are
Nice to
you?
see you again. I'm well. How are you doing? Thank you for your nice presentation. I just want to ask concerning the resistivity test. I'm going to ask two questions. The resistivity test, how reliable do you think the result is? And you said you have to
couldn't hear you. Can you say it again?
Okay, I was asking about the resistivity test. Yeah, how reliable is the result that you get from your resistivity test? Because you mentioned that you have to do the test when it is wet.
Yes, yes.
Okay, at what point is that? Because, you know, at different stages, the concrete can still be wet. But at what point would you recommend for the test to be done, and how reliable is the test? And then secondly, I want to ask about, maybe you have, I know of late people.
Let me answer the first question.
Okay, okay.
The reliability we have not studied in that terms, but
Okay.
this will give you a much better estimate if you wet the concrete, you know. But again, when I say if it is very porous concrete, let's say you wet it for 15 minutes, you might get enough water in, or at least the wetness, it will be good enough. But if you talk about a very high quality concrete, then the water may not, or the water vapor may not penetrate that much in that case. So it depends on concrete to concrete, I would say. So the idea is make it, you know, at least SSD condition. Or in other words, let's say you wet it for 1 day. If it is for a field structure. If it is talking about cube, you do it as soon as you take it out of the curing room, you do the testing before breaking the specimen. That will give you very consistent result. If you're talking about a field structure, maybe you may have to wet it for 1 day or something so that you can, you know, get, because you don't have to make the water go through it too much. Cover region is what we are focusing on. So that should be good enough is what I would say.
Okay.
And
Thank you.
one thing to note down is that when you talk about, you know, the positioning of the resistivity meter, it should be perpendicular to the steel reinforcement.
Right.
So we are developing a standard right now on a detailed standard is coming up on how to perform the resistivity test.
Okay. Thank you, Prof.
I can share you the draft document if you.
Okay. Just a quick one, Mr. Biola, if you don't mind. I see that people are proposing, I mean, in the US, this has been used significantly. I just wanted you to comment on the use of glass fiber reinforced polymers.
Bars.
Yeah.
Yeah.
GFRP bars. Yeah.
Yeah. So it's something which I think is promising, but there are a lot of challenges in ensuring the quality, and also it is relatively brittle in nature. So how do you make a ductile structure with a brittle material is a big question. So we may have to think of, may not be like, yeah, this is applicable everywhere, but there are elements where you could use GFRP bars where, you know, at least in India right now, non-structural elements they are allowing. Non-structural elements, and also on roads or the, you know, pavements where, you know, structure is not going to collapse or anything. So we have to specifically choose what type of elements are there where we can use GFRP bars. But recently in India, we have come up with a new design code, not design code. We came up with a new code for specifications for GFRP bars. And where we, you know, really look at the quality, because the fiber content is something very important to look at. If you don't have, I think 0.8 fiber content, it'll be very loose and, there are a lot of aspects which one has to look at and to ensure that there are enough, because there's different chemical usages, you can really play around. And
Yeah,
GFRP bar
exactly.
is something, it's not like steel where you have to invest a lot of money to make steel bars. GFRP bar, the investment is not that very high. You can, it's relatively simple, easier to manufacture. So a lot of companies will come. So before approving it, it is very important to make sure that the quality is ensured.
Thank you very much. Thanks.
Thank
So
you,
I can
sir.
share that document if you
Okay,
need.
I'll reach out to you. Thank you.
Yeah.
All right, thank you so much, Prof. We have 3 people raising their hands up. I would just want to appeal that we take this 3, then we close the session. So, Dr. Femi Yusuf, please. The floor is yours. Dr. Femi Yusuf, are you still there?
Thank you. Yes, I am. Thank
All
you,
right,
Prof.
okay.
Thank you for the presentation.
Hi.
I'm actually a consultant on a project where these issues are at the forefront. It's a project that's very close to the seabed, and they are looking at extending the life of the structures. Reinforcement corrosion is going to be an issue, definitely. So my question is, so basically they're looking at extending the life of the structures for another 20 years minimum, I think to 2048 or thereabouts. And they've done the non-intrusive tests. We are waiting for the results for that. But they're going to do intrusive tests to look at the state of the reinforcement, etc. But from some of the pictures, you will see that there's definitely going to be reinforcement corrosion. So the question I have for you, this is a little bit more technical because you generally spoke about how we can extend the life from a design point of view. But if we have a scenario where we want to extend life by a particular
Yeah,
year.
I actually had a few slides on that just
Okay.
because I didn't get enough time.
Okay.
I will share that right now if you
Yes,
allow me.
I was waiting for that. So just very quickly, which is applicable to my project. If we know we want to do 20 years from now, what will be your
Yeah.
what will be your
Let me show you,
recommended approach?
this thing.
Yeah.
See, if you want 20 years of life, by putting coatings and all that, you may find it very difficult. Okay.
Okay.
So, and interventions might be required. So one technology which is very good, or at least I believe in that, is this cathodic protection.
Okay.
And this is a beam which you see here. When you repair without cathodic protection, you create corrosion like this on the region which is not repaired.
Okay.
Adjacent region starts corroding. Okay. Then you have these type of anodes which are available in the market.
Okay.
If you need more help, we can talk separately also. I can help you with that.
Yes. As the project progresses, if I need support, I'll leave it to you.
Kolawala knows me how to reach me. You can talk to him and then we'll talk.
Thank you so much. Thank you, Prof.
So this one is, it is not like just a zinc piece. You can really, it is special material which has very high pH for, it should last for 20-25 years.
Okay.
And also, it should be able to accommodate the zinc rust.
Okay.
So it's not like you take a zinc and put concrete around and it will not work. Why I'm saying that is there are products in the market which are like that. Okay. So you see my slide, it says the third bullet, performance record of more than 20 years. That's the number you're asking for.
Yes, that's what I'm looking for. Thank you.
So if you look at a close-up, you can see this is like this. Very porous material, no sand. This is the zinc piece.
Okay.
And very porous, like spongy type material.
Okay.
And then when we did some laboratory studies on that, we found that different anodes which are available in the market are showing different life.
Okay.
Then we came up with a question, how do I decide what to use? So we call it gap test, GAP test. Okay. and then we have made specifications. You can use this specification, and we can give you the answers also, and then that will give you good life. And with respect to money, if you go with this galvanic anode, you can really get 70% or more life.
Okay.
Sorry, the savings in money.
Okay. Thank you so much.
So
Let
we
me
can
allow
have a
the
separate
others.
discussion. We can have a separate discussion
Yes.
if you
Let me
want
allow
to.
the others who have questions as well. Thank you.
Thank you so much. I think we might have a part 2 of this with the way things are going actually. Okay, Dr. Shola George, your question please, and try to make it as a prompt as possible. Dr. Shola George, are you still there? Okay, let me move. Okay, Dr.
I
Shola George.
actually have another meeting in 2 minutes, so.
Okay. I think maybe we should just Dr. Shola George. All right. I think at this point, okay, Dr. Akinda Onsi, are you there? Maybe we'll just make that the last one. And
yes, good afternoon, everybody.
yes, afternoon, sir.
And I want to appreciate the presenter, our speaker. We appreciate your presentation, very nice one. I want to ask maybe about 1 or 2 questions. If you have a reinforcement that is corroded already, you can see it is no more useful. How can we connect it again with, we're talking of retrofitting now. How can we retrofit to connect reinforcement to it, especially if we have to use, I think you talked about carbon too, carbon fibers. I don't know whether you discussed that.
No, I did not talk about that.
Okay. I'm only thinking, is it possible to use carbon to connect? And if we have to use reinforcement, what will be the best method of connection, especially because 2 ends of it are corroded and they are gone? What can we do to a kind of retrofit in that type of thing?
I would say if the rebar is severely corroded and then gone.
Yes, the rebar is gone already.
You should put additional reinforcement. You could put additional reinforcement.
Additional reinforcement?
Yeah, additional. See,
no, what I'm saying, how do we connect? I'm only looking at especially the connection points now.
Some of these things, if you could share a photograph or something, then it will be easier to answer.
Okay.
Yeah.
Okay. Yeah, I think okay, maybe Prof will just help us with maybe Prof.
Because my suggestion is, because you asked this thing, I must say I must give you what I know. I would say that look at the cross section. I mean, if it is severely corroded, let's say more than 10% of corrosion, if you see, I would say you should put a new reinforcement to compensate for that.
Okay. Thank you very much.
All right, thank you. And Dr. Adebakin, if you're still there, please. That will be the last
I'm there
one.
now. Hello,
Oh.
Mr. Sholageorge is there now.
Oh, okay. Dr. Shola
Sorry.
George, please.
Okay. So, good afternoon, sir.
Good
The
afternoon.
lecture.
Afternoon, sir.
2 quick questions. The one on cement content. You said that the more cement you put in concrete, the weaker it is against corrosion. That's a bit surprising to me. I thought cement is supposed to provide power.
I couldn't understand. Can you say it again?
That the more cement we have in concrete, the weaker the concrete is, possibly against corrosion. Hello?
No, I didn't understand. The most?
The more cement, the higher the cement content. That the concrete becomes weaker against corrosion.
Yeah, weaker in the sense it becomes more, or it becomes, see, chloride cannot penetrate through the aggregates.
Okay.
Right? Chloride has to penetrate through the interface between the aggregate and the cement paste and the cement paste. It cannot penetrate through the aggregates.
Okay.
Correct. So by common sense, if you think I want to increase the amount of aggregate so that I resist the chloride's maximum.
Okay.
But then your challenge will be to ensuring workability. Right?
Now, what about strength?
Strength we can get. You have aggregate, smaller size aggregate, you can get strength. That That is the trade, you don't have to worry about strength. I think you can still get strength with less cement. The bridge project which I showed, the cement content was 400 only, 410.
Okay.
Yeah.
Okay, let's leave that. What about this
So
water
the thing
potency?
is, when you go for that low cement content, you have to make sure that the remaining aggregates also, the particle size distribution of the aggregate also have to be looked at. So, and provide adequate super plasticizer so that you get adequate workability.
Okay, thank you. I'll
Whatever you
consider.
do, the concrete has to be workable. Then only you can compact it and then get the properties.
Okay.
It's not
Then
like you
the
keep
issue-
on reducing the cement but not do anything else. So
Okay, all right.
All right.
Now, the
Thank
issue of
you
water,
very
you
much.
also suggested.
I
Hello,
will
just
have to. I will have to leave now. So
Thank you very
All right.
much. It's been a wonderful session, sir. We would probably get across to you for another session.
yeah, I'll be very happy. I
Yeah.
didn't know that 60 people attended this thing. So
I suggest that people should turn their camera for screenshots. Turn on
Okay,
your
sir.
camera for screenshots. So Adebanjo, you can do that.
All right, sir. Okay.
I don't see Kolawala here.
It's actually
Here, there.
Walawale is here, is hiding behind the camera.
All right, hold on. We're still waiting for some persons to switch on their camera. Okay, let's see.
You have in
Just wait for
three screen.
Oh. Okay. Some persons are still coming up. Aha.
No, just take it. Just take it so that we don't
Yeah,
waste time
because
again.
of time.
All right. Okay. 1, 2. Okay, sir. We have it. We have it. We have it. Thank you so much for joining. Professor Kolawole, sir, please, could you just give us a vote of thanks?
Yes,
Thank you, sir.
thank you so much. I appreciate Professor Radhakrishna Pillai for that wonderful presentation. I know if you give him time, you can still continue to talk for the next 2 hours, and you will never get and you will never get bored. We know that we still have opportunity for you to talk to us. I really appreciate every one of you for joining this important meeting, and we want to assure you that by December we'll be having another series, that is the Concrete Matters 07. So once again, thank you so much, and I appreciate all of you. So if you are interested in the slides and the recording of this, I've already shared an official email with you. Kindly make a request, then we will share all this with you. Once again, thank you so much and enjoy the rest of your day.
Thank you. Thank you.
Thank you so much.
Thank you.
Thank you, Professor.
Thank you,
Have a
sir.
wonderful day.
Thank
Thank
you.
you, sir.
Thank you so much.
All right.
Bye, Femi.
Thank you very much,
Thank
bro.
you, sir.
Thank you, sir.
Thank you so much. Thank you so much.
Thank you very much, sir.
Thank you, sir.
Thank you very much.
Sir.